So what have you covered in the last week? What is it you'd like to go over tonight?
I told you last week that I haven't had pre-calc yet.
Okay.
So I don't really know what I'm supposed to be learning.
Oh, so that's right. You're not taking a math class at the moment, are you?
Yeah, I have it next semester.
Okay. What is it next semester? Is it trig or is it pre-calc? Do you know?
Pre-calc. Our school has like a combination of both, really.
Right, and the same way here in Colorado. And some of the schools take pre-calc the first semester and then trig, and some reverse it. You don't really need trig for pre-calc, or in other words, they can be taken in either order. So let's see. I'm trying to remember what I did last week. What did we do last week? We
did logs and exponent laws.
Okay, logs and exponents. Let me get my pre-calc book here, and maybe I can find a chapter on logs and exponents, and let's make sure you're good on logs and exponents. The only thing I need is some practice problems to give you. Hold on. All right. Express that logarithmically for me.
Okay. It would be log under 2.
Okay, I call that log base 2.
Yeah, log base 2 equals 3.
Where does the y go?
Next to the log.
Y is the argument. That's what I call the argument. I don't know if that's what they call it in the class or not. In other words, the secret to converting these is just to know that logs are exponents. So, in other words, I can always figure out how to write it. If I want to do it the hard way, I can say, well, I know the log is going to have to equal 3 because logs are exponents. And now I just have to figure out where the 2 goes and where the y goes. Well, that's the base. So that's always going to go down there. And the only place left for the y is to there. And if you're going the other way, then I like to memorize it as the number on the far left raised to the power of the number on the far right is equal to whatever's in the middle. So that would be 2 to the third equals y. Okay?
Yep.
So that's the basic. You got to know how to do that. What is, rather than have me make them up, let me look at some in my book. Oh boy. My book is for some reason my book is on vectors. You know what the definition of E is?
No.
E is equal to the limit of 1 plus 1 over x, all raised to the x power, as x goes to infinity. And let's talk about this a little bit, because you haven't had limits, but this is a person's first exposure to limits. in Precalc, essentially. Notice what happens here. As x goes to infinity, this thing gets closer and closer to 0. But this thing gets bigger and bigger. In other words, if I were to let x be 100, I would have 1 over 100 raised to the 100th power. And if I were to let x be 1,000, I would have 1 plus 1 over 1,000 raised to the 1,000th power. Well, it's not real clear where this thing is headed. In other words, one might come to the conclusion that this thing's going to be 1. Because eventually when x gets infinitely large, I'm essentially turning this whole thing into 1. And 1 to any power is 1. So one could conceivably think that that number would go to 1. But any number greater than 1 raised to the infinite power, in other words, if I took this number right here and raise it to infinity, what's the answer?
Infinite. It's infinite?
Uh-huh. So it's not real clear where this number is headed. I mean, this is a very, very interesting problem. Well, guess what the answer is? The answer is E, which is approximately 2.71. And then, just like the number pi, it goes on forever, and it's irrational. Why does it go to 2.71? Well, that's a good question. E is probably the second most important number in all of math. Pi is probably the most important, and E is the second most. Why? It's because so many processes follow that kind of model. Anything that changes is proportional to the amount that's there. In other words, population, radioactive decay, the change in the amount that's there is dependent on how much there is there. And so many things in life are like that, where they are dependent on how much is there, that E enters into our lives all the time. If you're compounding money, in fact, that's something we should talk about. I'm sure you've had this, and you probably need to know this. If you have annual compounding, I'm jumping all over the place, I hope you don't mind. I'm just kind of trying to cover subjects that I know you cover in Algebra 2 and that you need to know for Precalc. So I may jump around a little bit here. If you want to stick with logs and exponents the entire hour, that's fine with me. I'm willing to do that. Just let me know if I'm going in a direction that you don't think is the appropriate one to go. A little bit in the dark here, but anyway, if you have annual compounding, you've been taught that the amount after some period of time is equal to your starting amount times 1 plus the rate of interest that you're getting, all to the t, where t is measured in years. For instance, does this look familiar? Have you had this?
No.
You haven't had this? Well,
I haven't.
It has to do, it's probably, this comes after logs because you can get a lot of problems that you need logs, you need to solve them with logs. For example, if I started with $100 and earned,
I think your voice is cutting off now.
ooh, that's not good. How's this sound? Is that okay? Sometimes the audio can be a little bit fussy on GoToMeeting. It'll frequently put out a message that,
Yes.
is it okay? Because we can do the audio.
Yeah, it's just getting a little choppy.
Well, if it gets too choppy, we can do the audio by having me call on my phone, and I'll just call your phone and you put it on speaker and we'll do the audio that way.
Okay.
Normally, I have found the audio to be pretty good with GoToMeeting. Almost better than the fidelity of it would be better than what you would get if I used my phone. But my phone probably wouldn't have any choppiness at all to it. So just holler if my voice starts to go in and out. If you had $100 and you deposited it at 5% interest, so that R becomes 0.5, and you left it in the bank for 3 years, that's how much you would have. You would have 100 times 1.05 to the third power. And you'd stick that into your calculator, but you would end up with approximately $118, I'm guessing, if you were doing annual compounding. Now, let me think whether I want to continue on this line or I want to go back and solidify your knowledge of logs. Let's make sure you can solve some log equations, because this compounding interest, there's 3 different kinds. There's annual, and then there's more frequently than annual. In other words, you can find some banks that will tell you they'll compound it monthly. And there's a different formula for that. And finally, there is continuous compounding, where your money is earning interest based on the amount that is there all the time. In other words, they're actually compounding it every single second. And continuous compounding, I'm just going to write this because it brings in E, is equal to your starting amount times E to the RT. And this E is that 2.71. And again, that E is an important number and related to anything that is increasing based on the amount that is there. And that is continuous compounding. Populations tend to grow with continuous compounding, whether it's a population of rabbits or a population of people. It will grow based on this model here. Radioactive material decays based on this model here because it decays based on how much is there. So E comes into that also. Let's back up though here, because in order to solve some of the equations you get from these, you have to be able to solve logarithm equations. So let's see. I believe last time, let me think for a moment. If I told you that $100 increased to $500 at a rate of 5% per year, how many years would that take? In other words, I'm using my standard formula. The amount is going to be equal to your starting amount times 1 plus the rate, all to t, where t is in years. Well, they could give you this problem in this format where the unknown is the exponent. Whenever the unknown is the exponent, it's going to require us to use logs. Okay. Do you know how we would solve this problem? What would the first step be?
You'd have to get 100 times 1.05 to the other side.
Well, this t only is acting on the 1.05. So you're right, we need to do something with this 100. So let's divide both sides by 100. So now the problem becomes this. We still don't have an algebraic way of solving that. I can't tell you how many years t is that would increase my starting principal by a factor of 5. So how would I solve for t?
Could you add a logarithm to it?
Take the natural log of both sides.
And since t is an exponent, you can make it t natural log 1.5.
And what's the last step? Always remember that these are just numbers. That is a number. I may not know what it is. I may have to look in my calculator to figure out what it is, but it's just a number. So if there was a number in front of t, how would you solve for t?
You divide it.
Divide both sides by that number. So I'm going to divide both sides by the natural log of 1.05. And that is going to be the answer for t. Now, you can get this out of a calculator, and I don't know how many years it would take, probably 20 or 30. Here, do you have your calculator in front of you?
I don't have a graphing calculator yet.
Do you have a calculator that does logs?
Not with me. It's in my book bag.
Okay, let's use Wolfram Alpha, which is kind of my online calculator. Actually, you know what? Let's not use Wolfram Alpha. Let's use this virtual TI-84 that I have. This is probably something that you're more familiar with. Does this look familiar?
It's sort of. Ours are a tad different.
Yours are what?
Ours are a tad different.
Okay. If I wanted to figure out this ratio, in other words, natural log of 5 divided by natural log of 1.05, well, there's my natural log key. There's 5, end paren, divide by natural log of 1.05, end paren, enter, 32, almost 33 years. So if you put $100 in the bank and it earns 5% a year, at the end of 33 years, it would have grown to $500. In other words, it would have gone up by a factor of 5. That's if you're simple compounding. Okay. So that's how we do problems like compounding, is we solve them by using logs. Anytime you are trying to solve for the variable that's in the exponent, you're going to have to use logs. I mean, almost any time. Unless you had a problem like this. How can I do this problem?
Well, you could simplify the left side to 3 to the x power.
What would you put on the left side?
You do 3 with the square root
Right.
of x.
In other words, the only way I can do these without using logs is the fact that both of these numbers, 9 and 27, have a common exponential base, which is 3. I can write 9 as 3 squared in parentheses always to the x, and I can write 27 as 3 cubed always in parentheses to the 2x minus 1. Now, applying my rules of exponents, what's the left side become?
3 to the square root of 2x.
3 to the 2x.
Or,
In other words, what I'm doing here is what I kind of like to call double exponentiation. I'm exponentiating 3, and then I'm exponentiating the whole thing to x. And when you do that, you multiply the exponents. Okay? So the right becomes what?
3 to the 6x minus 3.
Okay. And now, because I have some number to an exponent equals the same number to a different exponent, I can basically equate the exponents. So I can say 2x has to equal 6x minus 3. And now if I solve that, I get 4x equal 3, x equal 3/4. Okay, so if I had a problem like this, I can solve it without logs. But is all I have to do is change one number, change that to a 6, and now how can we solve it? In other words, 26 does not have a common base of 3, so I can't use that same method. So now I got to use logs. And when you have to use logs, the first step is always to take the natural log of both sides. Okay? And now, using the most important property of logs, which is that that exponent can go down on the line, get x natural log of 9 equals 2x minus 1 in parentheses times natural log of 26. Okay, what's my next step have to be?
You would divide both sides of natural log 26.
Yeah, I can't quite hear what you're saying. What would you do on the right side?
I would divide both sides by 2x, or natural log 26.
Well,
Or could you simplify the natural log more?
there's a problem with doing it that way. And that, in other words, if I try to get my x's on the same side and all my logs on the other, I'm going to end up with a 2x minus 1 divided by an x. And then that's going to give me 1 minus 1 over x. I could see where that might almost be an easier way to do it, but that's not the typical way. The typical thing to do here is distribute to this. In other words, remember that is just a number. So if I made that 3.4, how would you solve the problem? You would distribute it. You would multiply that 3.4 times the 2x and also by the minus 1. So let's try that. And I'm going to I'll leave it like this. Minus natural log of 26. So I distributed the right side. And the left side I can leave like that for the moment. Now, notice that at this point, I want to get anything with x in it all on the same side, and anything without x on the other side. So how about we take this over to this side, and we take this over to that side? Well, what's that going to give me? That's going to give me natural log of 26 equals 2x natural log of 26 minus x natural log of 9. Now what's the next thing I need to do? Think of it as just an algebraic equation where this is a number. That's some number times 2x minus x times some other number.
You divide both sides by natural log 26 and natural log 9.
Actually, there's a better way to do it, and that is to factor out the x. Notice that my goal here is to end up with x equals something. Well, if I factor out the x, then I'm left with this. Now notice I'm getting a lot closer to the answer. I've got x times some number equals another number. So I can divide both sides by that quantity, and I've solved for x. So x is going to be equal to the natural log of 26 divided by, and I can either write this as 2 natural log of 26, or I could even write it as natural log of 26 squared minus natural log of 9. And now I have nothing but one variable on one side of the equation and nothing but numbers on the other. And that would end up being you'd obviously have to put this into the calculator to come up with a number, but that's not the important part. The important part is getting to this final spot. Let me take just a moment to find in my book some more log problems. Hold on a moment. Looking in my pre-calc book, and I really should have been looking in my Algebra 2 book. Yeah. Interesting. In my Algebra 2 book, one of the last chapters is exponential and logarithmic functions. And it starts out with exponential growth, then exponential decay, which we've kind of talked about. And then it starts out with about the number e. And then it goes into logarithmic functions and the properties of logs. And then solving exponential and logarithmic equations. And that's probably our best bet, is to practice solving exponential and logarithmic equations. Let's see if I can find some. Let's take this one here. How would you solve that?
Could you change it to log base 3 5x divided by log base 3 negative 1?
Remember that this is not a multiplier. That is not log base 3 times x plus 7. That is log base 3 of x plus 7. It's not the same thing as 3x, where 3 is multiplying times x. It's more of a function of x. In other words, if I write f of x, it doesn't mean f times x. It means a function of x. I have some function, and the variable is x. So, however, what do we notice here? We have the log base 3 of one argument, equals the log base 3 of a different argument, what can I say about the arguments?
Could you divide both sides by them to cancel them out?
Well, I can say the arguments have to be equal. If you want there's another process that let's talk about. In other words, I can say that 5x minus 1 equals x plus 7, and then solve it. And that gives me 4x equals 8, x equals 2. Okay? And so x equals 2. And then I need to check and make sure that that does not violate any domains. Well, if I go back to my original problem, we talked about this last time, didn't we, about violating domains?
I don't think so.
Oh, okay. You can only take logs of positive numbers. You cannot take the log of a negative number, and you cannot take the log of 0. So if you solve a log equation and it gives you an answer that violates one of the domains, then it's not an answer. But in this case, that does not violate anything, because that means we're going to be taking the log of 9, and over here it would be the log of 9 also. So in this particular case, we don't violate any domains at all. Let's see if I can find one that does, so we can talk about that. Hold on. Yeah, here's one that's a good one. We did talk about the log properties, right? Like the log of a times b is equal to the log of a plus the log of b?
Yeah.
Okay. So we worked with expanding and contracting these things, right? Okay. So what can I do with the left side? I've got two logs being added together. Can I turn that into a single log function?
Yeah, you can change it to log 5x multiplied by x minus 1.
Okay, let's distribute that. What do we get?
5x squared minus 5x.
And now to solve it, let's put it in exponential format. What's the base over here? Remember, start with that.
It's 10.
Okay. So what's the exponential expression of that?
I don't know.
Well, remember, it's the number on the far left raised to the power of the number on the far right, and it's equal to the argument. So it's 10 squared equals 5x squared minus 5x. Okay, now we can solve this. In other words, this is just an algebraic expression. That's a quadratic that I can solve. Well, notice that, hold on, 10 squared is 100. Divide everything. How would you solve this? Let's review quadratics while we're at it. That's certainly a huge part of pre-calculus, is being able to factor or solve any quadratic.
You would subtract 100 from both sides, so 5x squared minus 5x minus 100 equals 0.
Now what?
You could take out the common factor of 5, so it's 5 and then parentheses x squared minus
And in
x.
fact, I can just divide every term in the equation by 5. Because when I divide 0 by 5, I still have 0. So I can lose the 5 altogether. Do have to divide that by 5 to get that. Now what?
And then in parentheses it'd be x minus 5, and then another pair of parentheses x plus 4.
Are you good at factoring? Or are you? I'm just asking. I haven't really. I mean, you did this one pretty quick. Are you in general pretty good at factoring, or is factoring something we should practice also?
I think I'm pretty decent at it.
Okay, it seems like it. So what is your solutions?
Positive 5 and negative 4.
Now notice that if we go back up into the original, this one right here.
The only one could be positive 5 since you can't have a negative log.
Exactly. If x were negative, this thing would be negative. You can't, violates the domain. And so that alone causes me to throw out that answer right there. Does 5 work? Yeah, 5 works. It means it would be the log of 25 plus the log of 4 equals 2. Not violating any domains. And with log equations, you almost always have one of the solutions. In other words, the harder problems are always going to be kind of like this, where you're going to end up solving a quadratic. And a quadratic usually has a positive and a negative solution. And one of those usually violates the domain of one of these. Now, notice that it might not violate the domain of that. Or this. Does minus 4 violate that domain? It does not. In other words, minus 4 squared is 16 times 5 is 80 minus 5 times minus 4, which is 20, so that would be 100. So both solutions work just fine if I go to the compressed equation. And that's an interesting thing, because we're taught that this thing is the same as this thing, right? In other words, we're allowed to compress it into a single log function. But in actuality, they are not exactly the same. You cannot check your answers versus the compressed one. You have to check your domain violations on the original one. It would be a different story if the problem started out like this. If this was the problem and this was the first line of the problem, well, now both solutions work. 5 works and so does minus 4. So that's something to keep in mind, that for domain purposes, these compressions and expansions are not exactly the same thing. All right, that was a little tough. Let's find another one kind of like that. I'll let you try it. How do I solve this? Remember, when you're solving log equations, at some point, you generally need to put it in exponential format. In other words, I can't solve it in log format. But if I can turn this thing into exponential format, I'll be able to solve it easy. What is it exponentially again? Use some method of memorizing how you go back and forth between logs and exponential. That is the most important thing about logarithms and exponentials, is that you be able to go back and forth from either one to the other. Number on the far left.
Oh, you would do 5 to the second power equals 3x plus 1.
Okay, that's a good technique to remember by. At least it works for me. It's probably not what they taught you in class, but whatever technique you use when you're trying to memorize stuff doesn't matter. And now notice how easy it is to solve. So we have 3x equal 24, x equal 8. Does 8 violate that domain? No, it doesn't. And so we've solved it. Now, there's another technique that the book I'm looking at right now uses to solve this same problem. I don't know if I like it or not, but it is something that's worth learning. And that is exponentiating each side. What I mean by that is I can make this the exponent of anything I want as long as I do it to both sides. I can say 5 to that exponent is equal to 5 squared. I could say 4 to that exponent is equal to 4 squared. I can always exponentiate any kind of an equation. And the reason I did it to 5 is because we have this property that says b raised to the log base b of x is equal to x, always. Okay? So by exponentiating it to the same base, I'm guaranteeing that what I'm going to write on the left is 3x plus 1. And on the right, 5 squared. So I get to the same place as I got before. I'm just calling it something different. And it might seem insignificant that there's two different ways to do the same thing, but there are going to be problems where the only solution is by exponentiating both sides. It won't be possible to put it in exponential format like we were this problem. In other words, I don't really need to do this complicated exponentiating of both sides, because all I need to do is express that in exponential format. And it gives me the same thing without the difficult concept attached. We'll come across a problem where the only way to solve it is by exponentiating both sides. Let me look for some more problems here. Well, let me just give you some to solve. Remember that the step is always to express it exponentially. What's the number on the far left?
10.
Okay, so how would I express this exponentially?
10 to the 2.4 power equals x.
That's the answer. Now I have to put that into a calculator to figure out what number it is, but that's the answer. In other words, once you express it exponentially, you basically are solving it, especially a simple one like this. About this one.
3 to the third power equals 2x minus 1. So
Yeah,
x is
now it's a piece of cake, yeah. Now x is going to equal 14. Okay. We're always trying to isolate that. Once we isolate that, we can express it exponentially.
Would this one be 10 to the 44th power equals x to...
We don't want to express it exponentially until we've isolated the log part of it. I still got this 12 over here. What can I do with that 12?
You could bring it over so it's x to the 12th power.
I could do that, but that's going to make it more complicated. Why don't I just divide both sides by 12? Now I have a simple one. Now express this exponentially.
10 to the 40th.
This is natural log, not common log.
Oh. So would you take both sides to the power of 8?
Well, I don't even need to do that. That certainly accomplishes what I want to do. But the more direct way is just to express this exponentially. The number on the far left raised to what power?
4412.
Equals x. And there's my answer. I can get that number out of my calculator. Do you see why expressing it exponentially is actually a little bit easier? It gives you the same answer. Notice that if I did it the way you wanted to do it, in other words, exponentiate both sides to that, well, that becomes just x. And so I end up with x equals e to the 44 over 1 over 12. So it's not even a longer step. It's just difficult conceptually to exponentiate both sides to e. I don't need to do it here. All I need to do is express this thing exponentially, as opposed to exponentiating both sides. Okay, let's do some others. Now, these bases, if I have a problem like this, these can only be easily done, at least they can only be done the way we're doing them, because it's the same base. In other words, if this was log base 2 and this was log base 3, I'd have big problems. I wouldn't be able to solve it. So whenever you have multiple logs in an equation, you can only combine them, expand them, contract them, compress them, express them exponentially if it's the same base. Okay. Now, this is another case where I have the log base 2 of one argument is equal to the log base 2 of another argument. So therefore, what can I say? It's the same concept as if I say 3 to the x power equals 3 to the 2x minus 1. If I tell you this, then because the 3 is the same, I can equate that to that by definition. Okay? Well, this is a similar thing. I'm taking the log base 2 of one argument. If it's equal to the log base 2 of a different argument, what can I say about the arguments?
But they're equal?
Yeah. So x plus 2 equals x squared. And again, we just have a simple quadratic that can be solved. Let's go ahead and solve it. Because we're looking at a quadratic, so we know we're going to get two solutions. And one of those solutions may violate one of our domains. So until we actually come up with the solution, we can't really say we're done with this problem. So if I put 0 on one side, I've got this. Now what?
X minus 2, x plus 1.
So my solutions are x equal 2, x equal minus 1. Do either of those violate the domain?
Negative 1 more.
Not really. It's being squared.
But then none of them would.
Right. In other words, both of these solutions work. The log base 2 of 4 is equal to the log base 2 of 1. Whoa, they don't both work. Notice how when I tried them, even though it doesn't violate the domain, when I plug them in, it doesn't work. There's no way the log base 2 of 4, which is that side, oh yes it is, it's equal to the log base 2 of 4. When I square 2, I get 4. So the 2 works. Now let's try the 1. Well, the log base 2, when I substitute minus 1, I get the log base 2 of 1. When I substitute minus 1 for that, it turns positive. That's also equal to the log base 2 of 1. What's the log base 2 of 1 equal to?
Log base 2.
All logs of 1, regardless of the base, are equal to the same number. What is it?
Is it 1?
It's 0. In other words, the log base 2 of 1 is equal to 0. The log base 17 of 1 is equal to 0. The natural log of 1 is equal to 0. So both of these are equal to 0. So both answers work. I did not violate a domain. Now, notice one thing here. Had this problem been given to me, and instead of the 2 being there, it's in front, looks like the same thing, but now the minus 1 does violate the domain. I can't take the log, I can't do this right side. I can't take the log of minus 1. But that's not the way the problem was given to us. The problem was given to us like this, and as long as that's our argument, minus 1 works just fine. It's a little confusing and a little strange that we have all these compression and expansion rules, but they don't produce exactly the same thing with regards to domain. Okay, I solved that one.
You do 3x multiplied by x plus 2. And then you factor it, so it'd be 3x.
First of all, you got to multiply it together.
Yeah, 6x. 3x squared plus 6x. And then it would be 10 equals 3x squared plus 6x.
Good. Keep going.
And then you subtract both sides by 10. And then
now these are a little tougher to factor. Anytime there's a coefficient in front of the x, how would we try to factor that? In other words, when I factor something like this, I really do it in steps. I notice you kind of do the whole thing at once in your head. First thing I got to do is split up the 3x squared. And that splits up only one way, 3x and x. Now I know my signs are opposite, so it's either plus minus or minus plus, and it might make a difference. And now I need factors of 10. Well, there's only two sets, 10 and 1 and 5 and 2. And I'm betting 5 and 2 is the factors that are going to work. And at this point, I just kind of try them randomly. I start with 5 there and 2 there. Does that work?
No.
Not only does it not work, but it doesn't give us the right absolute value. It doesn't give us a 6 in the middle. Which means that there's no point in trying the 5 down here and the 2 down there, because that's going to give me the same number, just a different sign. So the next thing to try in this trial and error process would be the 2 there and the 5 there. Does that give you a proper middle term?
No.
Okay. Next thing to try would be 10 and 1. I can tell that 10 and 1 comes close, but it doesn't give me 6x in the middle. Which means 10 down here and 1 over there is going to give me minus 7x instead of plus 7x. So I might try 1 and 10, but I know that's not going to work, because when that 10 multiplies by the 3x, it blows up minus 30x. So I've basically come to the conclusion that it doesn't factor, right? I've tried all combinations. What's my next step? I still have to solve it. I just can't solve it by factoring it. What do you use when you have a quadratic that can't be solved by factoring?
A quadratic equation?
Right. What is it?
I don't have it memorized.
Okay, that is something you're going to want to memorize. A lot of schools teach a little song to people. I don't have a little song to teach you. The one way I like to teach it is the first half of it is minus b over 2a. That's the solution to find the vertex of a quadratic, is it not? Have you learned that it's minus b over 2a gives you the x coordinate of the vertex?
Yeah.
So if you remember that, then it's just that plus or minus the square root, and that has a name called the discriminant. B squared minus 4ac, it actually has a name, the discriminant. The reason it has its own name is because it's very important as to whether that's positive, negative, or 0. If it's positive, we're going to be taking the square root of a positive number. We're going to have two real solutions. If it's negative, we're going to be taking the square root of a negative number. Have you done imaginary numbers yet?
Yeah.
Okay. If the discriminant is negative, we're going to have the two imaginary solutions. And if the discriminant is exactly equal to 0, well, then this whole part would drop off, and I would have only one solution, and it would be real. There wouldn't be any imaginary numbers in it. So to come up with the solution to this, I would plug it in. And you know what A, B, and C are?
Yeah.
A is 3, B is 6, plus 6, and C is minus 10. So we're done with our hour. I don't want to go over. And that's a good place to stop. And we can kind of pick up from there next time. And I'll try to be a little more prepared as to where we want to go next. But I think I'll just kind of stick with my book and go forward from solving logs. Since you don't have a kind of an agenda, in other words, since your agenda is really just to review Algebra 2, that's what we'll do. Okay?
All right.
Now, I am going to close out this meeting before your brother comes on, so that you'll notice last time we had a 2-hour session, and when I recorded it, it came out as a 2-hour session. So if either you or your brother wanted to review it, it would have been difficult. So a better way to do this is to close out GoToMeeting at the end of each hour session, and then you'll have your own file that will review just this material that we've done, and your brother will have his own file also. But for me to do that, I've got to send a new meeting ID number. Now, the phone number that I called, was that yours? Was that a house phone? Is that something your brother has access to? Or is it a different number for him?
He has a different number because I use my cell phone.
Give me his different number. The 5626 is your cell phone?
Yeah.
Okay, and what is Saad's? Is his pronounced Saad?
Yeah, it's pronounced Saad.
Okay, what's his cell phone number?
His is 717 698 2028.
Okay, and I'm not going to call him. I'm just going to text him the meeting ID number. So you'll need to close out the GoToMeeting,